Welcome back everyone. In this lecture we will continue with the proof of Weyl character formula. For that purpose, first we need to define the Laplacian operator on this formal power series ring. So, let us define it and we will make some observations about these Laplacian operators. So, recall this q double bracket lambda by 2. So, this is the formal power series generated by e power lambda, where lambda comes from lambda by 2. So, over the rationals. Okay. So, one can actually view the element of this formal power series as just a formal power series in this variables e power lambda. So, f is in cube bracket double bracket lambda by 2, then one can write this f as summation a mu e power mu comes from lambda by 2. Note that lambda by 2 is actually a countable set. So, we are talking about only the countable sum. So, this summation is treated as a formal power series. Okay. So, for example, if you are planning to add a 2 power series, you just add them just to coefficient wise. So, this e power mu coefficients you just add them. Okay, let's actually define what is the addition and multiplication here. So, if you take these two elements f and g, so you write f equal to summation a mu e power mu and then g to be summation b mu e power mu, then f plus g is defined to be summation a mu plus b mu times e power mu. And what is the product? The product is given by convolution product. You take this product e power lambda times e power lambda dash to be e power lambda plus lambda dash and then extend this bilinearly. So, this is exactly summation a gamma b gamma dash, where gamma plus gamma dash equal to mu times this e power mu you run over. And note that to define this f g, we demand that this product indeed finite. Okay, this is indeed finite sum. Okay, and this is something ensured in the definition of formal power series. Okay, so we are not going to define very rigorously what it is and so on, but so what is more important for us to remember that, so whenever you want to do algebra in this formal power series world, so you can do as long as the coefficients are all finite, there is no issue. So, for example, so only problem that may occur when you take the product, so this part should be finite, then only you will be able to sum these coefficients and then make finite sum. And one can actually take, for example, logarithm, exponential, even derivatives, everything makes sense in the formal world, and those things make sense as long as you have these coefficients are all finite in that corresponding operations. Okay, so let us say we are working here and then we want to define this Laplacian operator, let us call it L. So, this is the operator that is defined on this ring, formal power series ring. So, which is given by this cube double bracket lambda by 2. So, the way you define this operator, you define it on the basis and then extend linearly. So, this L of e power lambda is defined to be the norm lambda square e power lambda. Okay, and this is for all lambda comes from lambda by 2. And most of the time we will be only actually dealing with elements which has finite supports. So, we do not need to really worry about these operators. So, now let us actually take this operator and then restrict to, for example, antisymmetric elements, and then there we want to make some observations. So, what we are going to do, we take this operator, restrict to this q bracket lambda. So, there we do not have any issue. For example, we can define this operator, extend this linearly, because everything is finite sum there. But then what we are going to do, we are going to further restrict to antisymmetric elements. So, let us restrict to the antisymmetric part of this q bracket lambda. So, what is this? By definition, this is those f inside q bracket lambda such that f is antisymmetric. And we have already seen that this is indeed a subring of this q bracket lambda, sorry, not subring, it is a subspace. Okay. So, the addition and then scalar multiplication all preserve this antisymmetric property, but product of two antisymmetric will be symmetric, okay, that we do not want. But this is a vector subspace. So, what is the basis of this? So, we already seen what will be the basis. So, if you take this Weyl sum S lambda plus rho, where lambda runs over all dominant weights, that will actually form a basis for this set antisymmetric elements of q lambda. So, let us call this is capital A, okay. And so, this is simple exercise that if you take this Weyl sums S lambda plus rho, where lambda comes from lambda plus. So, this form a Z basis. So, this form a Z basis of this capital A or q bracket lambda antisymmetric. Okay. So, this is more or less I proved it in the last class. So, the only thing that you need to actually verify is that S lambda plus rho, they form actually linearly independent set. So, we already said that it will form actually a spanning set for this antisymmetric elements, that is the computation I did in the last class. To prove it is linearly independent, you have to notice one thing about the definition of S lambda plus rho. The S lambda plus rho defined to be the sign of sigma e power sigma of lambda plus rho, where sigma runs over Sn plus 1. So, then you can easily see that this is indeed can be written as e power lambda plus rho plus some lower terms. What I mean by lower terms with respect to the dominance order, the sigma lambda plus rho is indeed smaller than lambda plus rho in the dominance order for all sigma inside Sn plus 1. And when sigma is non-identity, it is going to be strictly smaller. So, that actually kind of tells you that S lambda plus rho is given as e power lambda plus rho plus lower terms. So, now if you have some relations among S lambda plus rho, that will actually yield relations among this e power lambda plus rho, but e power lambda plus rho, that will form a basis, not basis, it will form a spanning set in it is actually linearly independent inside this q bracket lambda by definition. So, that will imply that this S lambda plus rho, they are all linearly independent. So, that proves indeed this is Z basis. So, now using this, you can observe that what it does to like in terms of this Laplacians. So, when you compute the Laplacian of this S lambda plus rho, it is not hard to see that this is indeed eigenvector for this Laplacian. So, just apply Laplacian on this S lambda plus rho. Recall that the L of e power mu is nothing but norm mu square e power mu. So, that is by definition of the Laplacian. So, now if you take this L of S lambda plus rho, then you can easily see that this is going to be the sign of sigma norm sigma lambda plus rho square times e power sigma lambda plus rho sigma runs over Sn plus 1. But what is this norm sigma lambda plus rho square, which is nothing but the inner product sigma lambda plus rho comma sigma lambda plus rho. But the sigma is coming from actually the Weyl group, which is Sn plus 1. So, but the Weyl group is generated by the simple reflections Si. So, in particularly the inner product is invariant under this Weyl group action. So, that means, so all these sigmas, they are all act as orthogonal transformations. So, they preserve the inner product. So, in particularly this is exactly same as lambda plus rho comma lambda plus rho, which is same as norm lambda plus rho square. So, now if you substitute that in this equation, then you get L of S lambda plus rho is exactly equal to norm lambda plus rho square S lambda plus rho. So, this tells you that if you apply this Laplacian on S lambda plus rho, then you get exactly norm lambda plus rho square S lambda plus rho. So, that means S lambda plus rho is an eigenvector corresponding to the eigenvalue lambda plus rho square. But there is something interesting about these eigen values. Okay. So, it is a simple exercise to see that for given 2 lambda 1 and lambda 2 in lambda plus. So, we have lambda 1 plus rho, the norm is same as let us say lambda plus lambda 2 plus rho square, if and only if this lambda 1 must be same as lambda 2. Okay. So, because this lambda 1 and lambda 2, they are actually coming from lambda plus. So, now, so we will be able to like because so you will be able to compare them. Okay. So, in case if lambda 1 is less than or equal to lambda 2, then it cannot be strictly less than lambda 2 with this actually equality. Okay. So, that is why like it will imply that whenever the norms are same, then that implies lambda 1 is same as lambda 2. So, maybe I will leave it to you to think about it, it is not very hard to prove actually. But then it says that, so if you actually take this basis S lambda plus rho, where lambda comes from lambda plus. So, this forms Z basis of this Q bracket lambda antisymmetric. So, this space, and this also consisting of eigenvectors of this Laplacian L. So, these are all nothing but L eigenvectors. So, that also forms a Z basis of this Q bracket lambda antisymmetric elements. So, this S lambda plus rho, they are eigenvectors for the Laplacians, and they also corresponds to distinct eigenvalues. Okay. So, that means in case if you are interested in proving the Weyl character formula, so then that can be reinterpreted as follows. So, now as a simple corollary, you can see that. So, what is the Weyl character formula? The Weyl character formula tells you that chi lambda must be same as S lambda plus rho divided by S rho. So, this is equivalent to saying that S rho is times chi lambda must be S lambda plus rho. So, this is more or less by definition. So, in case if you want to prove this, so then one can prove that S rho times chi lambda is same as S lambda plus rho. You can say that this is if and only if the Laplacian applied to S rho chi lambda. So, that is exactly same as norm lambda plus rho square S rho chi lambda. Okay. So, it is enough to prove that S rho chi lambda becomes eigenvector for this Laplacian L with the eigenvalue norm lambda plus rho square. So, if it is the case, then you can easily see that this will be written as sum of corresponding eigenvectors, okay, but we know that this S lambda plus rho is the only eigenvector of L that actually satisfy this condition. So, that forces that this S rho chi lambda will be same as S lambda plus rho. So, this is simple observation that comes from the observation that these S lambda plus rho, they are all Laplacian eigenvectors and they form a basis for this antisymmetric elements of this Q bracket lambda. So, that is the motivation to define this Laplacian. Indeed, we will actually prove that using Fradonthal formula that this thing is true. That when you actually look at this S rho times chi lambda, that becomes an eigenvector for the Laplacian with the eigenvalue norm lambda plus rho square. So, that is the computation that we want to finally do it. But before that, let us actually define one bilinear form on this formal power series ring, and we need it to do some computation. So, let us call it as a bracket. So, this is the bilinear form. So, that we want to define it on this formal power series algebra. So, what it is? So, this is by definition. So, you take some two elements Fg, and then because we want to define the bilinear form, it is enough to define it on the basis. So, let us actually define it on the basis as follows: the bracket e power lambda e power mu, that is defined to be lambda mu times e power lambda plus mu for all lambda mu inside this Q bracket, sorry, lambda by 2. So, we are it is okay to define it for the basis element and extend it linearly to all the elements. So, now one can compute the following. Okay. So, here is the exercise. So, maybe I will do it. So, here is the lemma. So, this lemma says when you take two elements F and G from this formal power series, and then if you take the product, how you compute that bilinear form on that product with some other element H. Okay. So, we more explicitly, if you take three elements F G H inside the formal power series, okay, this is good enough for us. So, maybe I will take it in the lambda by 2. So, then we have, so we want to compute what happens to the product F G, and then when you take the bilinear form on this F G comma H. So, this is exactly equal to F times G H plus F H G. Okay. And this is true for all elements F G H in your formal power series. So, this is something we will use later to compute what happens if you take the product S rho with some e power gamma. Okay. So, to do this, it is enough to actually consider H being some e power lambda. Okay. So, let us say that we just do the computation only. Okay. So, without loss of generality, just take H to be e power lambda. So, if you prove it for e power lambda, then it is by linearity you have done it for all the elements. So, what if we take H to be e power lambda? So, let us write F to be summation A gamma e power gamma, and then G to be summation B gamma e power gamma gamma. So, then you can see that what is F G. So, the F G is given by summation mu in lambda, summation A gamma B gamma dash, gamma plus gamma dash is equal to mu, times e power mu. So, this is what f g. So, now if you compute f g comma e power lambda the bracket. So, this is by definition you can easily see that whenever you take e power lambda e power mu, the bracket is nothing but the inner product lambda mu times e power lambda plus mu. So, what is f g times e power lambda? So, you have to just use the linearity and then bring it in. So, this is exactly equal to summation mu in lambda summation a gamma b gamma dash gamma plus gamma dash equal to mu. Okay. So, this is the coefficient that you are having for e power mu, then the bracket e power mu e power lambda comes. So, that is going to give you the inner product mu comma lambda times e power lambda plus mu. So, this is what you get when you apply it for f g comma e power lambda. So, now if you just compute what is g e power lambda. So, this is going to be exactly summation b gamma or gamma dash comma lambda e power gamma dash plus lambda, where gamma is dash is coming from. So, let us not bother about where the indexing set is running over. So, this is by 2 indeed. Okay. So, in particularly if you take f times g comma e power lambda. So, you can see that this is going to be summation over mu summation this. So, this f is going to give you a gamma and then this element is going to give you b gamma dash, but this gamma dash comma lambda will be there in the side and gamma plus gamma dash. So, this is going to be exactly so if you are interested in running over mu, okay. So, already this e power, so you can run over mu like this and then e power mu plus lambda will be there. Okay. So, it is good to have this e power lambda plus mu. So, that is the thing that we are having outside. And similarly, you can write down what will be the f h times g. Okay. If you write down f e power lambda times g. So, this is something you can work it out. This is going to be sum over mu summation again gamma plus gamma dash mu a gamma and then gamma times lambda b gamma dash times e power mu plus lambda will come. Okay, if you add these two, then you have to just look at the coefficient of e power mu plus lambda. So, that is the thing we need to equate. The coefficient here in this sum. So, this is summation a gamma b gamma dash times mu lambda. So, that is the thing that we need. So, you can see that this and this if you add, you will get exactly, this is exactly summation a gamma b gamma dash. So, then this thing will come as common, then gamma plus gamma dash will come here times lambda and then gamma gamma dash equal to mu will come. So, but this is exactly equal to summation a gamma b gamma dash times mu lambda, where gamma plus gamma dash equal to mu. So, this term is exactly matches with this term. Okay. So, that proves that this equality is true for all f g h. Okay. Now, let us see how one can use this to compute something that we wanted. Okay. So, as a corollary, so we can write down the following corollary. So, we take this S rho, which is by definition the sign of sigma e power sigma rho, sigma comes from Sn plus 1, which is also given by e power rho product 1 minus e power minus alpha, alpha comes from delta plus, which can be rewritten as product e power alpha by 2 minus e power minus alpha by 2, alpha comes from delta plus. So, now what we want to compute? We want to actually compute what will be the bracket S rho comma e power gamma or given gamma. Okay. So, you take S rho and then compute bracket S rho e power gamma. So, we want to actually normalize so that we will compute this twice of this. Okay. So, this is something we want to compute for any gamma in let us say lambda by 2. So, now the thing is S rho is being the product, if you write it as some F1 etc., some Fn, you can easily see that using this formula. So, let us recall the formula. The bracket Fg comma h is nothing but F times bracket GH plus bracket FH times G. So, if you actually think about it, by induction you can generalize that formula to any finitely many products. So, if you take the product F1 etc. Fn comma G, so this is going to be summation. So, this F1 etc. Fi hat etc. Fn times this bracket Fi comma G will come, where I range from 1 to n. So, this hat means you forget that Fi. So, this hat just means, so you omit that particular element, you omit Fi in the product. In some sense, this is just exactly the product F1 etc. F1 divided by Fi. So, that is exactly this omitting thing. So, this is just follows easily from the induction, because we are actually lambda and lambda by 2 both are abelian groups. So, we are working in the commutative ring. So, we do not need to worry about the order in which these things are written. So, this is true. So, now using this we can actually see that if we take this twice S rho comma e power gamma. So, this is going to be twice the product e power alpha by 2 minus e power minus alpha by 2, alpha comes from delta plus comma e power gamma. So, what is this? So, this is exactly equal to, so now you forget only the one thing. So, twice summation S rho divided by e power alpha by 2 minus e power minus alpha by 2, where alpha runs over delta plus. Then this will be the sum of these two terms, but note that e power alpha by 2 comma e power gamma, by definition this is the inner product alpha by 2 comma gamma times e power gamma plus alpha by 2. So, this is going to be exactly times alpha by 2 comma gamma plus alpha by 2 comma gamma times this e power gamma plus alpha by 2 minus e power gamma minus alpha by 2. So, this is the term that you get, sorry, this is plus. So, now if you simplify, so this is going to be twice alpha by 2 comma gamma. So, this so that becomes gamma comma alpha. Oh, I have written wrongly. So, this only one term will come out. So, this is going to be just alpha by 2 comma gamma, because this one gives gamma comma alpha by 2, and that one also gives minus alpha by 2 comma gamma, this minus that minus will get cancelled. So, then times e power gamma plus alpha by 2 and then plus e power gamma minus alpha by 2 comes. Okay. So, then if you just compute it again, twice S rho comma e power gamma is exactly equal to summation. So, now this 2 and 2 we can cancel. So, then it is exactly gamma comma alpha divided by e power alpha by 2 minus e power minus alpha by 2. So, this S rho comes out alpha in delta plus times e power gamma plus alpha by 2 minus plus e power gamma minus alpha by 2. So, this is what we get. So, again we can simplify this. This is S rho times summation alpha in delta plus e power gamma comma alpha divided by, okay. So, this is now it is like x plus x inverse divided by x minus x inverse. So, this is same as, so you can take out x there. So, x square plus 1 by x divided by 1 by x square minus 1. So, it is exactly this thing gets cancelled. So, that is e power alpha plus 1 divided by e power alpha minus 1. So, this is the term that we are getting. So, you just write it like this. So, that means twice S rho comma e power gamma is given by S rho times summation gamma alpha e power gamma e power alpha plus 1 divided by e power alpha minus 1, where alpha runs over delta plus. So, this is something that we will be needing later in the calculations of proving Weyl character formula. That will be good enough for us to proceed. So, if we actually take two elements f and g from the formal power series ring. So, then if we compute this Laplacian on f g, so then one can easily see that this is given by f into Laplacian of g plus Laplacian of f times g plus twice the bilinear form applied on f g, the bracket f g. Okay. So, to prove this again we will prove it only for the basis elements. Now, using the linearity, it will be true for all elements of f g. So, what is the proof? The proof is start with f is equal to e power lambda and g is equal to e power mu. So, then we just going to compute both side and then equate the things. So, you can easily see that the L of f g is going to be Laplacian operator applied on e power lambda plus mu, which is same as the norm lambda plus mu square e power lambda plus mu. And similarly, so what is f times L g, so which is e power lambda times the norm of mu square e power mu, so which is norm mu square e power lambda plus mu. And what is L of f times g, which is similarly norm lambda square e power lambda plus mu. And what is twice the bracket f g? That twice the bracket f g is given by twice lambda mu e power lambda plus mu. So, this is by definition. So, now the equality of this is clear from the following trivial equality, which actually given by this. So, norm of lambda plus mu square is same as norm lambda square plus norm mu square plus twice the inner product lambda mu. So, this is more or less clear from the definition. So, this proves that whenever you take the Laplacian on the product, that is given by this very explicit formula. Okay. So with this maybe I will stop here.